All right, review lesson number 2 as we work our way into this electricity and magnetism unit. Ohm's law, using Ohm's law in circuits. So determining missing values in circuits, being able to predict how much current will be here and how much voltage will be there and all that stuff. That's the plan. Apparently I've got a double page there. So we already saw this on the previous lesson. I'll just reveal all of it. In fact, I'll just reveal it later. But I mentioned how you can do Ohm's law calculations for any individual spot or as a whole, and that's absolutely what we are doing today in this. So change my mind. I'm just going to go ahead and get rid of those so I don't forget. And yeah, so in the questions, we're going to do it first. You're going to be given all of the resistance values and told how it's hooked up, given the voltage, and then you're going to predict how much voltage drops in each spot, which will correspond to how bright they'd be, how much current flows overall. Basically you'll know current and voltage everywhere, right? That's the goal to be able to do. That's understand how circuits work. You can figure out all those values, right? So the basic type, like I said, you're going to be given all of the resistance values and how they're hooked up. Your task is to determine everything else, right? So, for example, if you had a series circuit here scribbled in, we had 12 volts applied to a 2 ohm, 3 ohm, and a 7 ohm, you can calculate how much voltage drops here, how much current's through it, how much voltage drops there, basically everything, okay? Key steps. You need to calculate the total resistance, which we saw how to do yesterday. You then would just calculate how much current will flow. And then for a series circuit, you would need to recognize that the current is the same everywhere. So that total current would be the current through resistance number 1, which then Ohm's law is going to allow you just to do current times resistance gives you the voltage dropped here. Ditto, ditto. Lather, rinse, repeat at that point, right? For each of the series loads. So we know that current flows to each, and so we solve for each voltage. In a parallel circuit, you would instead know that the voltage across each load in parallel is the total voltage, right? And so you would have the resistance value and you have the voltage, and you'd solve for the current instead, right? So do that for each load in parallel, and you've got all of the information for that circuit. So this is the basic starting type here. And so, yeah, if you determine the total resistance, you're going to determine the current little flow, and then you're going to state the current little flow through each, because that's just something to recognize. So that part C is put in there as a helper for you. And then you determine the voltage, right? So do I have this all worked out? I forget. No, I don't. So let's do this. So we've got part A total resistance. In A, total resistance for a series circuit is just R1 plus R2, and certainly we'd say R plus R3 and plus R4 and plus R, and so on if there were more. But in this case, we just have resistance of 2 and resistance of 8, and so we have a grand total of 10 ohms of resistance. Part B, we get the total current little flow, so V total equals I total R total, right? Total voltage equals total current times total resistance. And so we've got our total voltage of 10 volts, and we've got our total resistance of 10 ohms, and we have this unknown total current that we want to find out. Just did some breezy numbers for us here just to get the idea across. But you divide out your 10 on both sides and get your total current is 1 amp. And part C, it says state the current that would flow through each resistance. Well, we know that basically current number 1, well, actually, let's say total current equals current number 1, and it also equals current number 2. Sort of the easiest way to sort of show that, right? And so then that means in part D, we have a total, we have, for part D, we want to look at the voltage across each part, right? So a V1, I1, R1, right, becomes, this is the same as total voltage. And so we say that really we have 10 volts. Oh, wait, I apologize. Current was the same. I got off track. Current was the same as the total current. So we put that in as a 1. So let me show that I total there. Thinking of a parallel one. Anyways, total current, right? So our equation becomes E1 equals total current times R1. You don't have to write that in, but your next line certainly would be having that value in, right? The 1 amp if you didn't show it specifically. Maybe you just do this, right? Something like this, where it's like, this is equal to total current, as a way to communicate what you've done. And then your next line can just be the 1 plugged in, and then the 10 for the resistance. And so you'd get, on this one, you'd have, resistance number 1 is just 2. And so we'd have 2 volts dropped on that first one. And then V2, I2, R2. And again, same deal, right? That's just the total resistant, total current. Oh my gosh, I'm having a hard time today. And so total current would be 1 still. Resistance number 2 is 8 ohms. And so you'd have 8 volts dropped on that one. Okay. So all of the things we've solved for this circuit, we've determined the total resistance. So I like to sort of box it in afterwards, right? So the total resistance, the total current, voltage across resistance 1, voltage across resistance 2, and also up here, essentially implied as a part of this, was that current number 1 is 1 amp, current number 2, 1 amp, right? So we've got all of the key things determined for that series circuit, right? When you look at this, then you'd say, okay, that means more energy was dropped off on resistance number 2, right? And so that one's going to be brighter. You look at this secondary thought here. This is which bulb will be brightest business, right? The voltage, of course, relates to the amount of energy. It is the amount of energy given off, so more voltage means brighter and so on. So the bulb, you can see what happened there is the bulb with more resistance in a circuit is, in a series circuit, that is the one that would be brighter. This is not how circuits are normally connected, mind you, right? So normally you just have a circuit with just a bulb, in which case this one would allow less current to flow, and so it wouldn't be as bright. So this would be your lower wattage bulb, but it would actually be brighter in series with other bulbs. It's just a true fact about how circuits work. In person, I show that, and it's kind of neat, right? But so many wonder, how do electrons know to share their electrons or their energy appropriately? If you think about it, the electrons, are going to feel how hard it is to push through this circuit, like how hard it is to get out of the grocery store, kind of thing, right? How much of a lineup there is, and then at this stage, there's only a little bit of resistance, and that's only 2 out of the 10 ohms, and then this is 8 out of the 10 ohms, so it's going to drop 2 out of 10 of the energy, and drop 8 out of 10 of the energy. You could just do it as ratios even there if you wanted to, right? But yeah, so this would be 8 out of a total of 10, and this would be 2 out of a total of 10, and so 2/10 of the energy, right? 2/10 of energy dropped. Whatever, something like that, right? And let's move on. The next part here. Oh yeah, this is the note about how a 2 ohm bulb would normally have less resistance, and therefore allow more current to flow, and therefore use more energy, and therefore be, of course, the brighter one, right? I already mentioned that in just verbally on the other slide there. Another example for practice for you, just let's go to the parallel stuff though. So same idea. We've got in this case though total resistance. So part A, 1 over total resistance equals 1 over R1 plus 1 over R2. So we'd have the total resistance, 1 over the total resistance equals 1 over 10 plus 1 over 40. Okay, so we could do this with decimals because it's nice terminating decimals, you call them, like they're not random ones where you have to round. So we got our 0.1 and we have our 0.025. If you weren't sure, of course, just do the numbers, but I mean 1/4 is 0.25, so divide by 10, you're going to be 0.025. But anyway, so I get 0.125. That's what 1 over total resistance is. So an easy math step for this is just to flip both sides, understanding this is over a 1, right? And so we end up with total resistance equaling 1 over 0.125, which you can then calculate, right? So 1 divided by 0.25, do I have 1 divided by 0.125. I don't know if I said that right or not, but 18.4 ohms. Something's wrong there. Let me fix 1, 5. I know what's wrong because it has to be less than 10. Let me just pause so I can not be problem solving too long here, but I will summarize in a second. Well, that was an easy fix. You probably already saw it. My calculation was just wrong, that's all. I did 2.3 or something like that divided by 0.125. The answer is actually 8, right? But man, it's a good idea to have the I'm glad that mistake happened, to be honest, because it's a good modeling there of like just having some understanding that's going to help you catch errors, right? Knowing that the resistance has to be less than the smallest one made it obvious to me that I'd made an error. And again, the 1 just wasn't typed in correctly on the calculator. So total resistance is 8 ohms. And now we're going to find the total current that'll flow. So part B, we have total voltage, total current, total resistance, Ohm's law version. And so we have total voltage is 12. We have the total current that we want to know. And we have the total resistance is 8. And so, of course, we're going to divide both sides by 8. End up with total current being whatever 12 divided by 8 is. So maybe I'll type it in right this time. 12 divided by 8 is 1.5. So we have 1.5 amps flowing. Okay. Part C says state the voltage across each resistance. In other words, know that the voltage number 1 is the same as or actually maybe I'll just do total voltage equals voltage number 1, which equals voltage number 2, right? So I might as well show it this time where, in other words, we're saying V1 has 12 volts across it. If you measure with a voltmeter, it would read minus 12 volts if you measure it correctly, showing that it's using energy, right? V2 is the 12 volts as well. Okay, so we've got these two known things here. We know the total resistance so far, we know the total current, and we know the voltages. So finally, in part D, if we want to know the current through each resistance, then V1, I1, R1, right, can become total voltage, right? So this is the same as total voltage. So that is a 12, and the current is what we're trying to figure out. So current number 1, resistance number 1, of course, is known. It's given as 10. And let's just assembly line this. V2, I2, R2. Again, 12 volts. Current that we want to know. Resistance is given as 40. And so we figure out how much current goes through each by just dividing both sides, right? Divide by 10 on both sides, divide by 40 on both sides. And there we go. So we end up with the 12 divided by 10 is just 1.2. And the 12 divided by 40, a little harder to do in my head, divided by 40, and it gives us 0.3. Now, what could have been done in my head, though, was to notice that the other 0.3, right, plus 0.3 would equal the 1.5. So that'd be another way to do this. You could say, or you could have said I total equals I1 plus I2, in which case you'd have a 1.5 here, you'd have a 1.2 here, and you'd have an unknown. Clearly we can solve for the unknown pretty easily there, right? We can take away the 1.2 from both sides and end up with I2 equals that 0.3. Now, if you do have numbers where there's rounding involved and so on, especially in calculating that total resistance and so on, obviously the more decimals you keep, the better. Or if you just work with fractions the whole way, which good mental exercise anyways. It's like brushing your teeth with your left hand if you're right-handed. Just keeps your brain active. But yeah, I digress. So another one for practice there, and then brightness. So in this one here, which one's brighter? Obviously here, this one's less resistance. It's going to allow more electrons to flow. It has more current and so on, right? And so in that one there, the 10 ohm has a lot more current. more electrons flow, delivering more energy, and so on, right? And another one worked out here. I'll just reveal that later. Maybe this is the one I was just going to show. Oh well. Same kind of stuff though, right? And get your total resistance, get your total current, get your voltage across each spot, and so on, right? So just reveal this. Move on here. I'll come back and reveal that before I go, I promise. Oh, there's the version of it already anyways. Let's just get rid of this then. There we go. Promise kept. Same deal for the parallel one here. You can reveal it bit by bit, but we've already done it. So good to go. Another one for practice there for you. Some worked, textbook versions worked out, same ideas. Same, all the way along. I want to get to the idea. Sometimes you're not just given the voltage in the R's in the resistances, right? So in this one, it says that this circuit has 7 amps flowing. Determine the voltage of the battery. It could just say solve the circuit, determine everything. How this would work is, let me check and see if I have numbers worked out for this one. I don't. So part A here, think about what we know, right? If we do our grasp method here, if we did our given, then we know we have the total current, and we have resistance number 1 and resistance number 2, right? So resistance number 1 is 12 ohms, resistance number 2 is 4 ohms, and we want to know the voltage, right? Well, you're going to have to sort of do a multiple step process where you're going to have to get from here, first you're going to have to get total resistance. And then after that, you're going to use all of that stuff to get V equals IR, right? Where we want to know the voltage, right? So let's do this. Let's move this one over. And parallel circuit, so we'd have 1 over RT equals 1 over the 12 plus 1 over the 4. And so that's going to calculate out to be a total resistance value, a certain number of ohms. And then at that point, you'll be able to say, okay, well, now we've got that certain number of ohms there, and we have how much current flows as a value given as 7. And so that's obviously just going to calculate to give us the voltage of the source. So that would just do the calculations. I'm just trying to speed things up a little bit here. And then determining the current of the bulbs, picture a V1, I1, R1. So resistance is known, voltage is known because it's the same as total voltage. And so you'd be able to get the current. And then same thing for V2. That's one way that a question can be a little bit different looking. Another, and a series version of this, what's true here, of course, is that the resistances add up directly, get the voltage, and then what's true after that is the current is the same everywhere. Okay? So same idea. I want to make sure to be able to get to and not have the video too long here, the idea of combination circuits. And so if you have a combination circuit, like an ugly one, like, where is it here? I'll show you. We have a combination circuit where it's not just series or not just parallel. So we have, in this one, we have parallel branches in series with other stuff. So we have series and parallel right away. And then in this parallel branch, there's series resistors there and so on. This is not as hard as it looks, okay? What I'm going to have as steps here is basically just combine resistances like crazy until you get the total resistance. So the 2 and the 3 obviously combines to be a 5, right? These guys would combine using the parallel. So now you have this is just a number. Now this, and this just add up. And so all of a sudden you have your total resistance. So the steps that I say here would be, get your total resistance, of course, right? And again, in this weirder circuit, it's the typical one where I gave you the applied voltage and I gave you all the resistances. If I didn't do that, then instead you might have current, and you just use V equals IR to find stuff everywhere you can, right? And eventually the puzzle all fills in. So total resistance, combine any little small bits you can. So if there's resistances in series somewhere, then obviously add them up. That is this section right here, for example. And really the 1, the 5, or the 1 ohm, the 3 ohm, and the 4 ohm, for example, would just add up as well to be, what's 8 ohms. So you could do that right away. So you'd be like, okay, I've got 8 ohms and I've got 5 ohms. So now I have a series circuit that's a lot simpler, where it's just literally an 8 ohm with a 5 ohm in parallel with a 4 ohm, right? So, and you can actually redraw the circuits if you want to, show it like the 8 ohm with the 5 ohm, the 4 ohm. You don't have to, but it certainly helps carry you through the process. Then you can do those, get that work, right? So then you're like, oh, that's actually 2.2. So now we have an 8 with a 2.2, which are clearly just going to add up to be a total of 10.22. Okay, so getting the total resistance, not really that bad. I'm going to jump ahead through these because I think that makes sense. And what did I have here? Add them up, right? Repeat that process until you have the total resistance. Kind of hard to word it, but I think it made sense looking at it. Then do your normal work, right? Use your total voltage, total current, total voltage and total resistance to get your total current. And then, just like normal, use your currents and voltages here and everywhere, right? So, for example, in this circuit, the weird one here, once you have how much current is flowing, well, then you can find out how much voltage dropped here. And you can find how much voltage dropped there. And you can find how much voltage dropped there. And then the remainder of the voltage is going to be dropped across this one for sure, and across those as a group for sure, right? So just putting it all together, it becomes not as bad as you might think. Step 4, the total voltages business, right? So get the voltages and so on. I think that's all you got to do for that, right? Current flows through each spot, get your voltages everywhere, and so on. I don't know if those steps make, like on their own, they're not as clear as, when you look at an example. So I'm just going to reveal them. We've talked about it enough. So I don't have the spaces on here to reveal step by step, but I think if you follow through, once we had that total resistance and we got the total current, notice how right away I was able to get the total voltage across here, and the total voltage across there, and the total across there, and then the leftover voltage business right here, right? Total voltage, take away all the individual voltages, gives us the voltage across here, which allows me to get the current through here, and then the rest of the current goes through here, and so on. Okay, so I hope that kind of makes sense. Yeah. So this is the kind where, you're given random bits, right? You might not be told everything each time. So this one here, notice that I did a little poll here. So notice that I gave you current and resistance here. That would allow you to get the voltage across that. And then you have voltage here and you have voltage there. So you can get the rest of the voltages on here, and that allows you to get the resistance and, just basically, use V equals IR to find pieces, and then just put it all together. And so that one's all worked out as well. Okay, so just working with Ohm's law like crazy, lots of little examples there to work out and try, and yeah, hopefully that makes sense. All right, thanks for watching. Talk to you later.